Hey guys, welcome to A-level chemistry and physics. And today we actually had a few viewer requests to do gravitational fields for the A-level syllabus for grade 8, grade 12. So this here it is. And in this topic, this will obviously assume that you have all the knowledge from the AS level syllabus and will therefore build on that. So yeah, you requested it, and here it is. So we first talk about a gravitational force. As we already know from our previous knowledge that a gravitational force exists by the property of mass. Any two bodies with intrinsic mass will exert a gravitational force on each other. This force is essentially dependent on only two things: the product of the two masses and their distance between them. So Newton put this forward as the law of gravitation, which states that any two point masses attract each other with a force that is directly proportional to the product of these two masses, but it is inversely proportional to the square of their separation. That means if you multiply the masses together, then the greater the product, the greater the gravitational force. And if you increase the distance between the two masses, the if the distance increases by a factor of 2, the gravitational force will decrease by a factor of 4 because it is inversely proportional to the square of the separation. So this is how we convert this into an equation. We use Newton's law of gravitation, and we know that force is directly proportional to the product of the masses. So if we take greater mass to be capital M, smaller mass to be small m, force is directly proportional to m into m, and force is directly proportional to 1 over r square, or force is inversely proportional to r square, where r is the distance between these two masses. So once we combine these two proportionalities, we get force is directly proportional to mm over r square. Now we know when we convert a proportionality into an equation, we need to put in a constant. This constant in this case is known as gravitational constant g, which gives us the equation F is equal to g mm over r square. This is a very important equation, and this will most of the first questions in the structured paper of the physics A level syllabus will include this equation. So it is a must. It is a must that you know this equation inside out. So then we come to the value of g. The value of g is the universal gravitational constant. When we say universal, we mean that the value of g does not change in any aspects of the universe. They can be at the in our solar system, beyond the solar system, around the Milky Way, so on and so forth. G will only have a constant value of, as stated, 6.67 and 10 to the power minus 11 Newton meter square per kg square. And so this gravitational constant. You'll have to memorize the value. It may just be in your data booklet. I'm not sure, but it is better if you just memorize it. It'll help you save time during your papers. So we saw a term point masses, that the force is directly proportional to the product of the point masses. So what do we mean by point masses? So gravitational fields are radial in nature. That means if you take the Earth, for example, the gravitational field lines extend outward from the surface of Earth due to its intrinsic mass. So if you take something as big as the Earth, it has a very large radius and is pretty much almost completely circular. It only bulges at the equator. So we assume that the Earth is a circular body. When we hypothetically draw the magnetic field lines for a body as large as the Earth, it appears as though the gravitational field lines are perpendicular to the surface. We will examine this in the next slide. There is a diagram. And if we trace these magnetic field lines back inside the Earth, it seems like as though they come out from the center of the object. Therefore, to simplify calculations and understanding, instead of taking Earth to be a body with volume, we instead assume that all of its mass is concentrated at its very center, and we treat a body as large as the Earth to be a point mass. So this is a great example. You see, these are the gravitational field lines, right? They are radially inward because gravity is an attractive force. If there is a body here, for example, it will be attracted to the Earth, and the Earth will be attracted to it because gravity is attractive in nature. This is the entirety of Earth's volume. And it seems like that the gravitational field lines are perpendicular to the surface, virtually at a 90-degree angle. So if we trace these gravitational field lines back, it appears that they converge at the center. So instead of treating Earth as a very large body, we assume that its entire mass is concentrated at the center, and it then becomes a point mass. It becomes much easier for calculations, for explanations, so on and so forth, and pretty much holds up in all situations. So, this is one factor that will hold true throughout your A-level paper as well. We come to gravitational field strength. So, gravitational field strength, as the name suggests, is the strength of the gravitational field. By definition, gravitational field strength at a point is the gravitational force exerted per unit mass on a small object placed at that point. So, if we place a random object within a random point in the gravitational field, we examine how much force it experiences and then we divide it by mass. At that point, the body has that the gravitational field has that gravitational field strength when we divide the force exerted on the body by the mass of the body itself. For reference, this is a very familiar number. The gravitational field strength of the Earth is 9.81 newtons per kg. That means for 1 kg mass, the Earth exerts a 9.81 Newton force on it. So then we come to the equation. As I said, gravitational field strength is force per unit mass. So G, which we take to the gravitational field strength, is equal to F, which is the force experienced by a body, divided by M, its intrinsic mass. Therefore, gravitational field strength has unit of Newton per kg, and this is essentially equal to meter per second square. We'll come to that. It's not, you don't need to know this, but it is essentially equal because it is g is also acceleration of free fall. So when you use the above definition to determine the gravitational field strength for a point in a gravitational field. Okay, so we know the gravitational force, as we saw before, is gmm over r square. We derived this in our previous slide using proportionalities. Gravitational field strength G is due to the mass m at a distance r from the center from the center of the object, right? That is G. So what we do is we make F the subject in this equation, and then F is the subject in this equation by taking m over there. So F is equal to mg, and F is also equal to gmm over r square. We equate these two equations. So F by m is equal to gmm over r square. This is done in a different way here, so you can do it like that. When you simplify these two equations, when you equate them, you will get g is equal to gm over r square. So the way to calculate gravitational field strength is the gravitational constant multiplied by the mass of the body generating the gravitational field upon the square of the distance between the body and the point at which the gravitational field strength is being measured. That's it. All you have to do is equate these two equations by making F the subject or M the subject, whatever you want to, however you want to do it. Solve it, and then you get G is equal to Gm over R square. Now we come to gravitational potential energy, right? And we've heard about it from our previous classes. We've even used equations, but there's going to be something different over here. So what's new? We're used to using GP is equal to mgh for calculations, right? That is the standard we've done, that's the standard way we've calculated in the previous years. But this has a few problems. So the first reference point is that when we use mgh, the h or the height from the surface assumes that the gravitational potential energy is zero at the surface of the earth. But what about the masses that are light years away? They experience negligible gravitational potential energy from the Earth, and it is almost impossible to measure the height. So once you have to when we have to talk about gravitational potential energy, we use Earth's surface as a reference point. That is not very convenient, right? We have to talk about a lot of things, greater distances, so on. So for very small distances from the surface of the Earth, like a few meters, it's okay because Earth's gravitational field is the only force being exerted on us. But when we are talking about objects light years away, which experience barely any force from the Earth, and it is impossible to calculate the height or the distance from the Earth, MGH becomes useless. Also, an assumption that is built in is that G, or the gravitational field strength, is constant no matter the distance from the Earth. Right? So as it's just common logic that if you move away from the source that is producing the attractive force of gravity, the further you move, because it is divided by r square, the force of attraction reduces. Therefore, the gravitational field strength reduces. However, in MGH, it is a built-in assumption that G is constant, which causes a lot of problems. Again, if you take an object that is billions of light years, that is light years away and like billions of meters or so, it becomes impossible to determine an accurate value of G. Therefore, we needed a new method of calculating GPE. So this is the new stuff. Now we change our reference point. Instead of taking Earth's surface to have zero gravitational potential energy, we we turn it on its head. We say that there is a mass at infinite distance from the Earth, and that is when its gravitational potential energy is zero. Okay, that's the reference point. That's a built-in assumption we're taking. Then what we do is we move it to a point closer to the Earth where there is a measurable force of attraction, and then we measure the work it took us, the work we did in moving the object from infinity to that point, because work done is equal to the energy transfer to that body. It's as simple as that. Object from infinity move to a specific point, and we calculate the work done on that body to move to that point. That is equal to the energy transferred. Now we come to gravitational potential and the difference between the two. So in practice, it is always more useful to talk about gravitational potential at a point. So gravitational potential essentially cancel. So if you have two objects, right, capital M and small m is just a multiple. At the same point, because of a different mass, it can experience different gravitational potential energy. So instead, at the same point, we calculate gravitational potential, which is GPE per unit mass, and then simply multiply the mass of the object in it, right? So, and the definition of gravitational potential at a point is the work done per unit mass in bringing a mass from infinity to that point. By contrast, gravitational potential energy is the work done in moving the mass from infinity to the point. In gravitational potential, it uses work done per unit mass. Gravitational potential energy is just work done, right? So symbol for potential is the Greek letter phi, and the equation is minus gm divided by r. Again, this is very important. And it is also important to understand the difference between gravitational potential and gravitational potential energy. We saw that there was a negative sign, and I assume if you're paying attention, there would also be a question that, okay, so I'll come to that later. So the existence of the negative sign is due to the reference point. Okay. When we take the mass at infinity to have zero gravitational potential energy, bring it to a point closer to the Earth's gravitational field and calculate the work done, we would observe that because gravity is an attractive force, we don't need to do any work on that mass at all. Instead, it would just move by itself because the Earth will attract that mass, right? So, how are we doing work? In fact, it is the gravitational force that is doing work on the object, right? So that's an intrinsic problem, right? How do you deal with that? So, how we tackle this problem is work done by the Earth on the mass is the negative equivalent of us doing work on the mass to bring it closer to the Earth, right? It's just the negative value of that. So if the gravitational field is doing work on the object, it's positive. Let's say it's positive 5 joules. So The field did positive 5 joules of work, bringing the object closer. So an external force did negative 5 joules of work, bringing the object closer to the source. That is how we tackle this problem. Since our reference point is the object doing work, we need a negative sign to compensate for it. So this is important. I'll just clarify a few terms. Gravitational potential, field, so on and so forth. So field strength is force per unit mass. Potential is potential energy per unit mass. This is important, and you should just memorize this because these are terms that will be widely used throughout presentations and papers and so on. Now we come to orbiting satellites. This is also an important part of the A-level syllabus. So forces in orbit. So as you already know, a satellite orbiting the Earth follows the principles of circular motion, right? You've probably already covered this in the AS level syllabus. So what this means is in circular motion, there is a constant inward centripetal force that is acting on the satellite towards the center of the orbit it takes. And the center in this case is obviously the Earth because the satellites are orbiting the Earth, right? So the centripetal force is towards the center of the Earth. However, the only force acting in the very same direction is the gravitational force because the Earth is constantly attracting the satellite, right? Because of the existence of gravity. Therefore, we can come to the conclusion that the centripetal force is actually being provided by the gravitational pull of the Earth. Therefore, the gravitational pull and the centripetal force are exactly identical for an orbiting satellite. So the calculation is also important. It talks about finding the velocity of orbit. So we know from again previous knowledge that centripetal force is mv square over r, where m is the mass of the satellite, v is its velocity, and r is its distance from the center of the Earth, right? So the centripetal force is equal to gravitational force. Gravitational force equation was g/mm over r square. Centripetal force is mv square over r. We equate these two and we make v the subject. So you'll do cancelling, you'll shift the variables to one side, and then rearranging will give you v square is equal to gm over r. So you just put in the values and then take out the square root. Also, do note that the small m gets cancelled out. And this is very important. So if you realize that if there is a satellite orbiting the Earth and there is an astronaut that comes out of the satellite for repairs, for example, the same astronaut and the satellite will orbit at exactly the same velocities because they're at the same height from the Earth. Otherwise, it will be too risky, right? The astronaut may just drift away. However, because the velocity of orbit is independent of the mass of the orbiting body, the astronaut does not face this problem. And along the same lines, we also find the time period of orbit, right? So um the orbital velocity is equal to the total distance by total time, right? That is how we find velocity, total distance by total time. Because it's circular motion, the satellite will trace the circumference of a circle, which is 2 pi r. So 2 pi r divided by time taken will give us velocity. Now from the previous equation, right, over here we know v square is equal to gm over r. V is also 2 pi r upon t. So we put this value of V in this equation, right? We square it and then we equate it to Gm over R. So once we square it, we get 4 pi square R square over T square is equal to Gm upon R. You make T square the subject of the equation and you get this expression. So you don't need to necessarily memorize it. It's just a logical conclusion, right? You can just memorize the logic behind it and you can derive it in the paper itself. It's not that hard. And yeah, you'll get this equation, and many a times you can be asked to calculate the time period as well. This is how you do it. Geostationary satellites. This is also asked often in the paper. So what is a geostationary satellite? Just continuing basic etymology, geostationary, which means it's by definition a satellite that stays exactly above a fixed point on the equator throughout the Earth's rotational period. So if there is a satellite, geostationary satellite right above you, It'll look like as though it is above you throughout the 24-hour cycle of the Earth. That's a geostationary satellite. And this is very important, okay? So there in the paper, the examiners will literally ask you what are the properties of a geostationary satellite, and then you'll have to give three, 4 pointers. So these are the 4 pointers that are there. Number one, it has a 24-hour time period, right? Because if it has to stay exactly above a point on the Earth all times, it will complete one revolution of the Earth in 24 hours, whether a revolution of Earth takes 24 hours. It always travels from west to east, and as I previously said, it is always directly above the equator, exactly above the equator, all the time. It has only one particular orbital radius. It never changes its radius or its height from the Earth's surface. It is always at one constant point above the Earth at one specific height. So literally just memorize these four because they'll always come in the paper. Yeah, so that's all, guys. Thank you for tuning in. And there was also another request, I believe, for another A level video. I will be doing that very soon. It takes me about 2 to 3 days to make the entire PPT, collect relevant information, so on. So I'll do it as soon as possible. And yeah, so this was a viewer request, and here it is. Thanks for watching. I'll You can put down any more requests in the comments below, and you can send me any of your doubts in the it's the email for the doubts is in the description. Thank you for watching. Bye bye.